Okay, let's begin. I'll close the door so we don't all go crazy from that alarm. I'm not sure who that's for. Like, does that mean we're supposed to be evacuating? Or are the fire department supposed to be here? It just has never been clear to me because it'll go off for days and days at a time and just nobody seems to hear it but me. I don't know. Maybe it's in my head. Anybody else hallucinating, hearing an alarm out in the lobby? Yeah. All right. Well, so we've got our final faculty candidate coming to campus on Monday, and there will be a presentation similar to what many of you attended last Friday, and so that'll be Monday of next week at 2 p.m. next door. And I'll offer a similar deal as last time, that if you attend and provide a brief write-up about what you learned and what your impression is, then you can get 10 bonus points towards homework. The faculty candidate who's coming told me, I gave them I think a list of 6 topics for the teaching demo. Happens to be that she selected the same topic as Dr. Fatah did. So I'm sorry to say you probably won't learn anything new about coagulation flocculation, but maybe. I mean, there's only so many things you can say about that topic, but the point is, if you'd like to attend, I would really be pleased to have you there and interested in your feedback, but if you're not able or not interested, then seriously, no problem. It's an optional thing if you'd like to come. Homework 2 is due next week on Wednesday. And then I haven't written it on here, but it is on our schedule for the semester that a week from today our class meeting will be online. It'll just be a lecture video that I'll post online because I'm going to be down in Greenville attending a meeting of the NCES working on questions for the FE exam. So we won't have class next Friday. Today we're going to continue talking about Chapter 8, just circling back to the design example we rushed through a little bit in class on Wednesday. And did I take 1 extra minute on Wednesday? I'm trying to remember. So I owe you 2 minutes today. I'll try and remember that. We're also going to talk about some empirical methods besides the Darcy-Weisbach equation. We'll go into some details about the Manning's equation and Hazen-Williams. So lots of good stuff today. Any questions about the announcements or anything else before we begin? So let me just refresh your memory. Last time we had this major pipeline with a secondary pipe connected to it. And we knew in that example the flow rate that we wanted to go through that secondary pipe, 300 liters per second. We knew because of the pressure differences that occur between the outlet and the major pipeline, what the head loss through the pipe would be. Its physical length of the pipe was known, its pipe material and roughness, all of that was known. And what we were trying to do is decide what diameter this secondary pipe should be. And we have this equation that relates diameter as a function of it being a circular pipe and applying the Darcy-Weisbach equation. But the challenge with this equation is that D, as you can see, depends on F. But then if you look at the Jane equation, which is what we use to estimate the friction factor F, F depends on the diameter and also the Reynolds number, which itself has diameter embedded there as well. So we've got some circular reasoning where we can't know the diameter or the friction factor because they both depend on each other. So do you remember what our strategy was to cut through that knot? We guess. We make a guess and then we check to see if the guess was good, and if it wasn't a perfect guess, we gradually improve over time. And so that's an iterative process we'll use a lot this semester for problem solving. When we've got too many unknowns, we'll start with a guess, see where things end up, and then improve over time. So let me refresh your memory on what that looked like. Here at the top of the spreadsheet was just all the physical constants that we know, like the flow rate, the equivalent sand roughness of the pipe's length, G, the head loss through the pipe, kinematic viscosity of water. And we started with kind of a lousy guess of F. I just wanted to make the point that even if you don't make a good guess of F, that eventually, through this process of closing the loop, we'll iterate and converge. Converge means that we have evidence that the solution is narrowing in on the correct answer. And the convergence criteria that we look for in an iteration like this is that the F value guess isn't changing anymore from step to step. That's one piece of evidence. And then the other is that the diameter has stabilized and that our guess of diameter from one iteration to the other isn't changing anymore. So if both of those things are true, if the F has stabilized and the guess of the diameter is stabilized, then we say that our numerical solution has converged. So we started with this guess of the F value, and then we used the equation to find out what's the diameter. And if that is the diameter, and knowing what we do about the flow rate, we'd calculate the area, the velocity through the pipe, the Reynolds number, and then we updated the F value based on the Jane equation to find out, well, if the water really is going that velocity through that diameter of a pipe, what F value should we expect? And it's a pretty big difference between our initial assumption and our updated guess. And so we did a second iteration saying, well, instead of this wild guess of 0.008, let's start with our better guess of F as the input in iteration 2. So iteration 2, we did the same steps. We used this equation to re-estimate the diameter. So now how have things changed from iteration 1 to iteration 2? Our first guess was basically 0.14. Our next guess was 0.17. So it's changing still, like on a percentage basis. I don't know, what is that? About maybe 20% it's changed, maybe a little less. So, but it's changing too much. We want it to lock in and not be changing anymore. So we update now our Reynolds number and velocity based on this new diameter. We find a new F value, and the F value didn't change as much from the input to the output of iteration 2. It started with 0.023 and it finished with 0.022. So it's getting pretty close, 5% change in this most recent iteration. So we just keep going through it. The F value now changing less than 1% within iteration 3, and the diameter 0.171, 0.173. So it's also showing signs of converging. And so in the fourth iteration, what we find is that the output diameter of 0.171, that's the same from iteration 3 to iteration 4. And the F value also stabilized and converged. So we could do more iterations. We could do an iteration 5, 6, 7, but nothing would be changing anymore. So we say that the solution is converged, and this is our answer. This is how big the pipe needs to be. So with that diameter of pipe, then the water will go 300 liters per second. If we used a bigger pipe, the water would flow at more than 300 liters per second. If we used a smaller pipe, the water would flow at less than 300 liters per second. Either way, the head loss is going to be 45 meters. That's the driving force that's getting water to go through that secondary pipe spur. So they probably don't make a pipe at exactly this diameter, right? So what we need to do is ask the client, so do you want to put a valve on here and so that you can get exactly 300 liters per second? Or do you want to get and if the answer to that was yes, then you'd get a slightly larger pipe. And you just use the valve to control the flow, the valve at the end of the pipe. If they didn't want to put in a valve and maybe 300 wasn't exactly what they needed, maybe 280 would be okay. Then maybe it would be okay to downsize the pipe. So you have to think kind of in logical terms when you get some odd pipe size like this. Should I go to 0.15 meters? Should I go to 0.2 meters? If you undersize, the flow rate would be less. If you oversize, the flow rate would be greater. And maybe that's a good thing, maybe that's a bad thing. So we can deal with it either way. But that's the iterative process that we can follow to know exactly what diameter is needed. Does anybody have questions about the process that we applied in this example?
Any questions at all? This is accurate. This method is very accurate, especially because we're using the Darcy-Weisbach equation. We're using the Jane equation within the range that it's intended for. So we could swap out Jane and use Colebrook instead, but it wouldn't improve things. So this is a fully justified application of Jane, and we get good results. This is the so-called easy way of doing it. This is an explicit equation that you can estimate the diameter just by substituting in the things that you know about the pipe. So what makes this easy is the fact that we don't have to iterate. No spreadsheet required. But it also looks kind of hard. Lots of opportunities for a mistake. So let me give you a taste for that. Let's pause for a minute, and I'd like you to try using this formula to find out, for the same conditions that were described here, and we came up with, the answer was 0.171 meters. So let's try using this formula for the previous example. So let me write the parameters on the board for that previous example. We had K sub S. K sub S was 0.00026 meters. The length of the pipe was 40 meters. The flow rate Q is 0.3 cubic meters per second. H sub F was 45 meters. The kinematic viscosity of water is 1 times 10 to the minus 6 meters squared per second. Okay, and of course we know G, 9.81 meters per second squared. I bet I'd be delighted if half the class gets this right. I mean, you know what you're looking for. You're looking for about 0.17 meters. But it's just so easy to make mistakes in an equation like this. My recommendation to try and avoid those mistakes is work in steps. Don't put the whole thing into your calculator all at once, but calculate kind of like intermediate quantities. Like find the result of what's in the bracket here and then double check. And then take it to the 4.75 power and so on. All right, so I'm going to pause the recording. I'm going to stop talking, give you some time to calculate here. Okay, so you're taking things to some exponent and adding it, and then to another exponent, and you know, another thing that makes this a little bit tricky is making sure that you put the right units into the equation. This one, everything should be in their traditional base SI units, and so K sub S should be in meters, not millimeters. Flow rate should be in cubic meters per second, not liters per second. So everything needs to be in its base units here. And whereas the iterative approach told us 0.171 meters, this explicit estimation says 0.175. So, I don't know. There it is. We've got some methods to estimate the pipe diameter that's needed when we know the head loss that's going to go through the pipe. That's not always the case. I think more often what we're trying to find out is what will be the head loss if we use a certain diameter pipe. This setup that I've just given you, this example we worked, it's important for us to know, but ordinarily the circumstances would be reversed. And we do our analysis on the basis of just checking different pipe diameters we have available. You know, like if you can get a commercially available 4-inch pipe, what's going to be the pressure downstream if you use it? And then deciding whether or not we should upsize or downsize the pipe after we look at the results. Any questions about this before we move on? So we've been using the Darcy-Weisbach equation, and it's very accurate. It's applicable over a broad range of conditions and fluids. We could use it for water, but you could always use it for other liquids as well. Anything that you know the viscosity for. But the downside of the Darcy-Weisbach equation, it's actually hand in hand. It's the downside, but it's also the reason why it's the most accurate, is because the F value responds to the flow condition. That's what makes it so accurate, is that the friction factor is more truly representing reality. I mean, the reality of flow through a pipe is that the effect of the pipe wall in causing pipe friction depends on the velocity, the diameter of the pipe, the material. There's a lot of factors that it depends on. And the other more simple methods that don't have a variable F value, the more simple methods, what makes them more simple is that the friction coefficient is fixed. That's not realistic. So it's a simplified model of reality that we like because of its simplicity, but we don't trust it in those situations where accuracy is really important. So Hazen-Williams equation is the best known and maybe the most useful of these other methods. Its limitations are that it only applies to water, so we couldn't use it for glycerin or alcohol or diesel fuel going through a pipeline. Hazen-Williams is just for water. That's okay. That's what we use the most in civil engineering. It's only applicable over a certain range of pipe diameters. So 50 millimeters, that's 5 centimeters, which is about 2 inches. So most of the pipes we'll deal with are bigger than 2 inches, but not all. Probably the water pipe to your house is smaller than 2 inches in diameter. So I had to replace my water pipeline 2 years ago, and the plumber was suggesting, I don't remember exactly, I think he was suggesting a 1/2 inch pipe, and I just figured I'd double check the calculations because I have a really long driveway and I'm up on a hill, and so I knew that pressure could be an issue potentially, and I found that the 1/2 inch pipe was not going to be big enough to get the flow to my house that I wanted, so we upsized to a larger pipe diameter. I couldn't use the Hazen-Williams equation for those calculations because the water pipes that I was considering putting in, they were smaller than 50 millimeters. So I had to use Darcy-Weisbach when I did those calculations. So Hazen-Williams is good for like municipal applications. It's not good for big industrial applications where you've either got a really big pipe or maybe an in-home situation where you've got a really small pipe. It's also, interestingly, the viscosity is fixed for water at 16 degrees Celsius. And why that temperature? I guess that's just the temperature that water is often at, that it flows through municipal pipes. And a velocity of 3 meters per second or less. So the reason why it's easier to use is that the friction factor, C, you just look it up based on what the pipe material is. And so, you know, ductile iron pipe would have 1 C value, and there's no Moody diagram. There's no Jane equation equivalent for the Hazen-Williams equation because you just look up the C value off of some table, and it's the same regardless of the flow conditions or situations. So you can see that here the equation is expressed both in the traditional units and SI units, and so we can rearrange the equation to solve for what is the velocity of water going through a pipe when you know the hydraulic radius, you know the friction coefficient, and then remember S sub F, slope of the energy grade line, is defined as the head loss divided by the pipe length. That's S sub F. So if you think about water flowing through a horizontal pipe and it's going from one location to the other, what's driving the water in the rightward direction, why water is moving from 1 to 2 is a pressure difference. That's why the water is flowing. So how big of a pressure difference is going to dictate the velocity of flow through the pipe. So if you were given a difference in pressures, then what you do is you'd find out how much energy loss is that equated to as the water goes through the pipe. And so you could substitute it in here to find the velocity of flow. Sometimes you'll know the velocity and you'll be trying to calculate how much energy loss is there for a certain velocity. So these two equations are the same. It's just algebraically we've rearranged and solved for h sub f, and you don't see directly h sub f in this formula, but it's built into s sub f through this relationship. So that's where the length parameter comes from, and that's how we solve for the head loss due to pipe friction. So British gravitational units just has a slightly different coefficient in front of it. That's stuffy in here, right? Any questions about Hazen-Williams equation? Let's get some practice. So we've got a tank that's open to the atmosphere, and the water surface elevation is 103.5 meters. So we're setting that as location 1 in the energy equation. It's where we know something. We know how much energy there is in the tank because we know the elevation of the tank above some datum, the elevation of the water in the tank above some datum is 103.5. So if the water's flowing from the tank through the pipe and to the spigot, location 1 is the tank where the pressure is 0 because it's vented to the atmosphere. Z at location 1 is the water surface elevation. The velocity of the water that's just sitting there in the tank is 0. Between 1, which is the tank, and 2, which is the spigot, there's no pump between those 2 points. And so we cancel out the pump term. The pressure at 2 is what we're trying to find. What is the pressure at the spigot? And what we're talking about is just before the water comes out of that valve. Because once the water vents to the atmosphere, like once the water comes out, it no longer has any pressure. So we're talking about just before the water comes out, what's the pressure inside the valve? That's P2 is unknown. Z2 is given because we have the physical elevation of the valve. V2, it says here you can assume the velocity head is negligible. So we're going to just cancel out the V2 term, even though we could calculate it because we know the pipe diameter, we know the flow rate. So the water still has velocity as it's going through the valve. So this gives you the instructions that you can assume the velocity head at 2 is negligible. And h sub f, that definitely is not negligible. There's plenty of energy loss as the water goes through that pipe. And this Hazen-Williams equation is how we're going to estimate the magnitude of head loss due to pipe friction. So let me pause. What you need to do is substitute values into the energy equation and substitute values into h sub f. And what we're solving for, the unknown we want to know is P2. So water's flowing from a tank through a pipe to a valve that's going to discharge it into the atmosphere. And we want to know, just before the water comes out of that spigot, how much pressure does it have? When the water is flowing at 11 liters per second through this 0.1 meter diameter pipe. So the equation that we're using for energy loss, Hazen-Williams equation, we need to know the velocity of the water through the flow. That's one of our first steps, is to find out how fast the water is moving. So from the diameter we get the area of the pipe, and then from the continuity equation, that's what this one is, Q equals VA, that's the continuity equation, we find that the velocity is 1.4 meters per second. Okay, so it's moving along in the water, it's losing energy as it does so. Of course, there's an elevation difference too that we have to keep track of, but the head loss due to pipe friction is 17.54 meters. If we put it into the Hazen-Williams equation for the given C value of 130. Did it say what kind of pipe that is? Iron, cast iron, pipe of 130, CH of 130. Okay, so now you can see how I've canceled out the energy equation Since the water's flowing from a vented tank, the pressure head at 1 is 0. The water inside of the tank is stationary, so the velocity head at 1 is 0. It does have some elevation that we're going to need to include. There's no pump between 1 and 2. I accidentally canceled out P2 here as I was working through it. That's actually what we're trying to solve for, P2. Elevation at 2 is applicable, and I told you to neglect the velocity head. I'll show you in a minute why we're able to do that. So rearranging that to solve for P2, we get that the pressure head at 2, the pressure at 2 is 303 kilopascals. I think it's a good idea when you do these calculations not just to write the number in the formula. You notice how every time I substitute values into the formula, I also include the units. I think that's a pretty important habit to avoid making mistakes. It takes up more space, and so you have to factor in the cost of the pencil. But I do think it's a good investment of your time, because if you've got like the wrong units in there, I think you're more likely to see it if you notice when you're writing the units next to the number. So like it would be easy, for example, if you were just seeing, okay, 11 liters per second, Q equals 11. If you put 11 divided by the area, you're less likely to notice that you've made a mistake if you don't write the units. But if you wrote 11 liters per second, and then you wrote the area in terms of square meters, then you're going to see the issue. So I'm going to try and be a good example this semester, and in the examples that I show you in class, I'm going to try to remember to always include the units. I'm tempted when I'm in a hurry not to include them, but I try and avoid that temptation because I'm prone to making mistakes just like everybody else, and you're less likely to make them when you include the units in your intermediate calculations. So pressure at 2 is 303 kilopascals. So why could we neglect the velocity head here? We do know what the velocity is. Let's just see how big is the velocity head at 2. So at location 2, the velocity head, V2 divided by 2g, the water was going 1.4 meters per second. Square that, divide it by 2g. 2 times 9.81 meters per second squared. So the amount of energy that's there is 0.0999 meters. That's the energy head that's like kind of wrapped up in the velocity head at location 2. And if you multiply that by gamma to get the pressure, like if this is the head, then pressure is gamma times the head. It is equivalent to 0.98 kilopascals. So if we hadn't neglected the velocity head, then, and if we did include it, then it would actually be 302 kilopascals instead of 303. So you can include it. It's not wrong, but it changes the final answer by less than 1/3 of 1%. So this formula is not accurate to within 1%. So like if we're doing things quick and easy by using the Hazen-Williams equation, then we might as well continue with this quick and easy approach and neglect the velocity head at 2. All right. So any questions so far about applying the Hazen-Williams equation when we're trying to find the pressure downstream? All right. Well, let's take a look at another example. This one, we're using the other form of the Hazen-Williams equation. Remember, one form of it we use to calculate the head loss. But if we know the head loss, we can use it to calculate the velocity. So here we've got, again, water flowing from the same elevated tank through the same 100 millimeter diameter pipe to the same spigot. But this time we want to find out what's the maximum flow rate that we could achieve downstream. So what is Q? through that pipe. So what you're going to need to do, substitute the things that you know into the energy equation. And when you know the pressure at 1, the elevation at 1, the velocity at 1, and so on, what you'll solve for here is h sub f. And remember, the slope of the energy grade line, S sub f, is h sub f divided by the pipe length. So start with the energy equation, then solve S sub f, then substitute it into here to find the velocity, and then substitute the velocity into the continuity equation to find the flow rate. Okay, one more thing I want to clarify. By free flow rate here, location 2 is just outside the spigot. You know, in the previous example, we were trying to find out what's the pressure inside the valve. This time what we're saying is, take location 2 just after the water is discharging from the spigot, so the pressure at 2 is 0. P2 is 0. So the elevation difference is driving water through the pipe. It's the energy that's overcoming the flow resistance. And there's going to be an equilibrium. Like the flow resistance is going to be in equilibrium with the amount of elevation difference, and the flow rate through the pipe is kind of like the deciding factor in how much energy loss there is, and the amount of energy loss is going to be equal to the elevation difference. So the head loss that's available to drive the flow through here, 48.5 meters. The slope of the energy grade line is the head loss due to pipe friction divided by the pipe length, 0.06381. Remember, for a circular pipe that's full of water, the hydraulic radius is simply the diameter divided by 4, so 0.025. It's the hydraulic radius. All right, now we need to substitute it into the Hazen-Williams equation. So 0.849 times the coefficient of friction 130 times the hydraulic radius to the power of 0.63 times the energy grade line slope to the power of 0.54. And I think when you do that, you should get that the velocity through the pipe is 2.444 meters per second. And then once we know the velocity, we multiply it by the cross-sectional area of the pipe, 0.7854 times 10 to the minus third meters squared, and we get it's a flow of 19.2 liters per second. So that's the most we can get through that pipe. If we need more, we could put in a pump. We could make the pipe diameter larger, or we could raise the tank. But this is the equilibrium that will arise for free flow through that pipe, as described by the Hazen-Williams equation.
Are the units for seconds just included in the constant?
Yeah, this is not a dimensionally homogeneous equation. This empirical equation, you magically come up with meters per second when you put things in here. Like, what is hydraulic radius to the power of 6.3? You know, like, what are the resulting units of meters to the power of 6.3? It's effectively meaningless, the units. So this is just an equation that was derived by observation. Okay, so there's also the Manning's equation, which we won't talk about today because I'm letting you out 2 minutes early. But there's a table in your book that has the friction factor. So be aware that you can go to the text to find the C sub H values. All right. Have a good weekend. I will see you on Monday.